All right. All right. We got everything online. We're back for another week. Another Haskell hacking session. This week, my friend, we are going to finish our little prototype for our kind of like event-driven backend for a REST API. So if this is your first time tuning in, no worries. The project is basically that we have a REST API we're building that uses like a Postgres database, a typical kind of web application maybe. And the event-driven part that we're building is using our Haskell library that we developed on this stream called Replicant. And Replicant is a client that can connect to a Postgres database and stream changes out of that database using the replication protocol. Now, we wrote a little service, and that service listens to that replication protocol for those change events. And it maps those change events from the domain of database changes to tables into our domain of provisioning routers, because we're basically building like a pretend cloud controller service or cloud service or whatever you want to call it. So let's open up our project. And this week we're basically going to look at just kind of, I don't have a, whatever. This week we're going to look at kind of rounding off the design of the service that actually calls into the cloud API. But we're just going to kind of like fake it just to make it look like a thing, and then we'll just kind of look at it end to end. So it's going to look, we're going to talk about a little bit about how to model this stuff in Haskell a little bit. So here we are, lib. Okie doke. Watch all the files there. LSP. Oh, that's cool. This is our like the source code for our little service. It's kind of hacky, but it it is what it is. Our main entry point over here listens to the logical stream of changes. You don't have to use replicant this way, but it does give you like a with logical stream function. And when we get a command, we eval it. And we change, we have a from change, which I almost feel like it's some kind of functor thing. But I'm no category theorist. I am just a hacker. Okay. So we go from change to the realm of changes to the realm of commands, so to speak. All right, and that's our router commands, like provisioning router, renaming a router. Those are the two we wanted to start off with. We could also implement add subnet. Okay, string, that's like a router ID, and maybe we have like a subnet, maybe it's string parse into something better, but we could add more router commands. But these are the two we're gonna focus on for now. All right, provision the router, rename the router. So provisioning comes from the insert SQL command. So when you insert a new row into our table, we're going to interpret that as a provision command. So we're going to go provision a new router on our cloud service. And this update, we map that update when you change the nickname of the router. So any kind of SQL insert update statement that changes the nickname, we're going to get that out and interpret that as a rename router command. Cool. So now all we need to do is to actually like evaluate these commands somehow and go and do those things on the cloud service. All right. And so this is kind of like a bit of like hacky together, probably pseudocode that we talked about in the last session a little bit. It's like how to turn that into how to interpret those commands, right? We have some kind of evaluation for those commands. Here, it looks like we're just doing like straight router command into an IO kind of thing. Put the da-da-da-da. But we also want to kind of like make this easier to test, right? And we don't actually want to call into our cloud API in our test suite. At least in our local development test suite, we might want to run some integration tests in a staging environment or something like that, or sandbox environment, which is another context we want to evaluate our commands in, right? We want to evaluate them like just locally in quick unit tests. We want to evaluate them in a sandbox environment where we have like special sandbox keys, perhaps. And we also want to interpret them in production, like with our actual API calls, with our secrets and everything. And logging and the whole 9 yards. And so the general gist of that is that we don't necessarily always want to run in the same IO. We want to be able to switch that out to make it easy to change the interpretation of what to do. Right? And that's what I mean by like interpret. Like when I interpret a command, you tell me to, like, we've been talking about domain-driven design kind of concepts and this idea of like event-driven design and stuff, right? And a lot of the things I'm trying to hammer home is that when you give a command to something in domain-driven design kind of areas, it'd be like giving a command to an aggregate, or which is like our cloud service here, right? And one of those commands is like provision the router. And one interpretation of that is that, okay, I'm actually going to go out and do that thing. But another way I could interpret it is like, oh, you just want me to like tell you what I would do if I was going to go out and do that. Right? Like I'd do a mock kind of run of the cloud, of the calls I would make to the API when you tell me to do that command, that kind of thing. And so we could provide those different interpretations by changing out the monad. Now, there's a couple of different ways I've seen in Haskell code for doing this. I don't know which one is better or worse. For the most part, they are roughly functionally, like behaviorally equivalent in some sense. And maybe somebody who knows a little bit more about the differences between the two can speak up. I know some of the differences. I kind of get what they're getting at, but in practice, they don't matter that much. So when you encounter those sorts of things, I find that's when people have a lot of really strong opinions about stuff, because it's like really easy to have an opinion about. But again, there might be subtle differences you might want to be aware of. So one way we could abstract out this IO and for these router commands is we can use, now this has nothing to do with tagless final encoding, so we could use like a tagless final encoding, or basically I'm going to show you a couple of different ways of doing this. One of those ways is with using a type class. Okay. And you'll find this when you're working with like MTL style code and things like that, or if you're already familiar with it, it takes the type class approach for a lot of these kinds of actions. And I find like in domain-driven design kind of ideas, where we're talking about like separation of like commands and what their effects and what they do, it kind of gives you a good space for naming the kinds of effects you need to run. So I feel like it'll kind of work well for this service as well. All right, so let's get rid of our old eval stuff here, our test eval stuff. We'll rewrite it basically. Okay, I think the rest of the stuff we need. So we have router command. We want to write a type class that will help us abstract over this monad. And so we can provide different, for each instance of this, we can provide a different monad for each instance of this class. So this will be like our router. Let's just go right ahead and call it the cloud service. This is the domain of our problem. Thank you for the follow there, 6FT Dan, or 6 feet Dan, I think. Correct me if I'm wrong, but yes, much appreciated. All of the follows here on this channel will help you get notifications if you want of when I go live. And we do some Haskell programming. Also just good feels too. Family's expanding. The agency is growing. So yeah, like we could eliminate, we've been talking about this idea of the bounded context, right? Of our design, of our system here, right? Of our service. This border of things. What is it? Right? Maybe this is like the cloud service. This is the cloud service context. Cloud controller context, or what have you. Right? And then one of the things you could tell it is to provision your routers, right? Provision the router. And one of the things we can do is we can add subnet and those sorts of things. So some external thing can tell us to do that, and then we'll go and interpret that and do the thing. So we're just going to provide different monads in our cloud service. We're going to abstract over the monads that are going to be available in the cloud service. So I'm going to call it cloud service for now. I'm going to start mixing things up. Keep you on our toes, right? And then one of those things we can do is provision a router, right? Now, the provision router, we can be we can be fairly specific here. We can say like, it can take a router command, and then we just have to make sure that when we're implementing this, we implement the right router command or provision router, the one we meant to provide. Or another way we could do this is we could just pass in those settings here. So like the nickname and the I think that was supposed to be like the MAC address or something. And then what does it return though? It returns an M, and maybe it even returns the state of like the cloud router that gets created, that gets provisioned, right? What is that? Like, I don't know. Cloud router, you know. Cloud router has, you know, an ID. Again, we're just using a lot of strings here and stuff to avoid like, it's just prototype stuff, but you know, you can even put it as like a little alias there. All right, it's a string. Whatever, right? So that might be the schema of like what it returns back to us when we execute the command successfully. If we could encode our errors here in the return type as well, which is probably something we should recommend doing, like, you know, either there's a cloud error or there's a cloud router we get back. That's right. We can add a subnet to a router. And then again, we either got a cloud error. Yeah, maybe this time we just get unit. All right, so this M here now is abstracted over. It's a type parameter of our class. Which means we need it to provide an instance of this class in order to use these functions. All right, which means we got to provide concrete versions of these functions, the ones that have the M filled in. All right, so provide an instance of the cloud service in IO. All right, or provision router is like provision router IO. And add subnet. Similarly, is add subnet. Yeah. Right. Or if we're using MTL, maybe we have a type class for HTTP calls, and then we know that the cloud service is only going to make HTTP calls. It's not actually going to like write to disk or any other random stuff. We can even provide like a stack of monads here with logging and other features available. Just being really, really simple right now, just to show you the idea, general gist of it. So there's our cloud service IO, so that means we need to just provide implementations for provision router IO, which is going to take our string. Now instead of M, it's going to be IO, either cloud air or cloud router. All right, leave that there for a second, and then we'll fill in add subnet similarly. Our unit. And that should be IO there. Cool. So here's now where we can actually do like our API calls. For now, you know, maybe we just want to kind of like see that it's kind of working. So we're gonna like just put strlen provisioning router. All right. Router ID, or what was it? Router name. If I could type, that would be great. And I'll fill that in here. Router name. If router Mac. Again, these are all. It's not an actual cloud service, like haven't. We're just kind of demonstrating how we could write a cloud controller like this using something like Replicant. So we pretend that we've gone and made an HTTP call in our IO monad here. Same thing with subnet, as subnet. You know, router ID and subnet. Right. Yeah, I'll just burp that over there. Adding subnet to router ID. And subnet ask subnet. Cool. Right? But now, oh, and that M should, sorry, be IO here. So now we can provide an instance for a different monad. So we have one for IO, but you know, maybe we just want to mock up our cloud service here. We don't, you know, we're a local development test, we're just asserting properties or contracts about how the types interact, or that certain combinations of our programs or whatever we're building here. We don't care about actually calling it, which we just care that like the actions that we expected to happen perhaps happened. So we just want to collect the fact that we're going to execute this action maybe instead of actually executing it. All right, so our cloud service could be like a state of like our mock state. All right, and then provision router would be like a mock provision router. or stub provision router, maybe. I don't know. People get really, really picky about the difference between mocks and stubs in some circles. I'm not too picky about it. I think as long as, you know, when you're writing any kind of testing, you're just trying to show that you've thought about the problem and your code faithfully implements your spec and what you want it to do. Your spec is like what you, the behavior you expect your program to have and how it should react to its inputs and the kinds of invariants it should hold. Right? So sometimes you can prove those things with types. Sometimes you can prove them with tests. Stubs, mocks, whatever, as long as, you know, you can get the general idea across in a straightforward way, and people can be satisfied that your solution is sufficient. It's usually good enough. So yeah, stub subnet, stub provision router. So these are going to be in our state monad. So let's call that stub provision router. And it's going to have, again, a lot of the same types. So it's a little boilerplatey. State, you know, our mock state, whatever that's going to be, and router, our cloud router, I should say. Stop provision router. What's that going to be? I don't know. Let's just leave a little hole there, have a little hole. And subnet, our state, mock state, and unit. Hey, Beavish, welcome back. Yeah, so to catch you up, Beavish, we're building a prototype or like a mock-up of a cloud controller kind of service. We have the idea is that we have a REST API that lets you create various things. Right. Routers, virtual machines, whatever. I also call this the data plane. And back here we have the control plane, the messiness. All right, so in the control plane, so the REST API just has your data models, your routers, things like that. Your resources. And on the control plane, that's where you've got to like your business logic. When somebody creates a router in the service, we want to actually go off and make a bunch of API calls to like provision the router and build it in the cloud service. And then maybe we update the state of our resource as we do these things. Same with like adding subnets and that kind of thing. So the way we implemented the REST API is that we just used PostgREST, which is a handy dandy, super cool program that can read a schema you give it in a Postgres database and generate an API for you. So that part in our prototype is done for us. We don't have to worry about it. We just write the schema tables and set all that up using PostgREST, and that's good. And then we use the library we wrote on the stream, PostgreSQL replicant, to listen to the replication stream, right? In real time, streaming replication events. And we listen to those on the control plane. So the control plane then reacts to those things that are happening in the database. Right, so when we insert a row, we map that to our control plane domain, like the provision router command. And then we're just writing the interpreter now for interpreting those commands, like provisioning routers and implementing and adding subnets and all the other things that you can do. All right, so it's a high-level view of the project. You're welcome. So yeah. So now if we want to be able to add like kind of test versions of these things for our local development purposes, when we're building the service, we're just going to create these little stub ones, kind of just as an example of a way you could stub out stuff. It's not the way you should, but a way that you can. All right, let's define mock state. Maybe mock state could be just a new type. And that could just be a list of strings. And derive some base classes for it. Why not? Right, so when we do this stub provision router, we're going to basically come up with kind of a convention for generating the stub provision string so that it shows the arguments in the strings, and then we're just going to append that to the list in the mock state. So that when we run this, we could just run this in using the state monads run function. To run our programs, right? To run our example programs, whatever we're testing. All right, so that would look like with our provision, like we got a router name, router MAC, whatever that is, and then, well, we don't have to have a do here. We just modify. Modify takes a function that modifies the state and some return value. I believe that's what it is, if I remember correctly. So we got to return a cloud router. All right. Yeah, what did we define our cloud router as? Just has the router ID and MAC, so we can just pop that right in. We can just be like test router and like the router MAC. All right, and then here, right, what are we getting? We're getting S, which is going to be our mock state. So I actually don't really need that. We can just go get mock state. Right. Once we get the mock state, we can do something with it. We can append our string to it, the string we want to append. Yeah, we're going to do something up, but then we've got to wrap it up with back into our mock state new type wrapper. All right, so this hole here. Are we getting that? No, it's just doing that silliness. So, data list. Don't want reducing lists. I don't want to like cons them at the front of the list. Do we have append? I forget. We got plus plus. Yeah. Whatever. Let's do that then. And we'll put our arguments here. Provisioning. Name. I don't know, router MAC. Something like that. We're going to basically do kind of the same thing for add subnet. But instead of provision routers, add subnet. And we got to do the subnet arguments. So that'll be router ID and actual subnet mask. Be like the show instance of that type. We only need to return unit. Yeah, cool. So this kind of, we'll just make a little helper for that. I'll call it a pen stub event or pen stub. String you want. Mock state. It'll return. Not quite what that function does. Because we have get mock state on the front. We'll take a mock state string and return the mock state. If we had like a functor for that, that would be just dandy because that's pretty much what we're doing. But just gonna pull all of this out. Yeah, well, let's put the string first. I'll just call it S. That'll be this string here. And that should be good. All right, then I can we just call pen stub. String we want. That should be good. That should be redundant. So let's get rid of that. Happiness. Happiness has been achieved. There's peace once again in the land. And let's make the same modification here. And stub. Remove that. Remove that. That should be jolly good. Cool. So that's roughly how we could do that. Show you, let's just test that out, see what that looks like. See if we get a bunch of errors, because LSP hasn't been running, but hasn't been running. Yeah, so we just need import state and define a few things. Cool. So let's import full.monad.state.script. And that makes that happy. Oh, it's a member of MTL. Sure. Sure. Okay. Yeah. Thanks, Haskell mode. Did. Restart. Okay, cool. Oh my gosh. Let's update our package then. MTL. That's fine. Good. Okay, let's get back there. Yeah, started. Cool, that's better. All right, I didn't ever define cloud errors, so let's just make that an alias for now. Type. Sorry, not alias. What am I doing? String. All right, subnets not in scope. Oh, this is what you should do for a lot of stuff. Just go ahead and make a new type for subnets. Subnet masks. Let's just derive eq and show for it, because we used show function a fair bit on that. Types in them into instances. Okay, that's probably for instance of state mock state there. Yeah, let's be a little flexible with that. I just got to fix the types on our returns here. Right, because we wanted either. So I went ahead and did that. So let's go fix those types. Going a little fast there. So we get the either, and then buried in the either, or buried in our state monad, we have either a cloud error or router for provisioning. And in this case, we have either cloud error or unit for adding subnets. The IO ones might be annoyed with us. No, we did put error either in those. So that's okay. It's cloud router. And something is still using eval command over here, down here, yeah. We no longer need eval command here. Well, we're not going to need it. I'm just gonna do this for now, just to make that go away, so we can focus on what we need to focus on here for a second. Did mean put. Sure. Fine, just print. Yes, that's what I meant. And lastly, ooh. Right, modify here is not happy now. Okay, that's really annoying, LSP. Like, it doesn't know how to read the stack environments, so it's not finding the modules here, which is completely messing up all of the error reporting in the editor here. Not happy with that. However, we're still getting some of these when we try to load into GHCI, so that's something at least. Yeah, so our stub functions are just not doing... I probably just got modify messed up here. Control Haskell control monad state strict. Yeah, get put state modify. Modify returns unit no matter what. Okay. So then we just have to provide the function. Okay. So then that, it kind of looked funny, right? Because we really want to return the pure of that cloud router that we did in test. Cloud router, name, well, it's not name, but test router ID, I don't know, like that. Yes, I can do there now. Pure is upset with us because we're buried a monad deep here. Sorry, not router, right. There we go. Right, so pure means like the state pure, the state monad here, which needs to return right. I'm not in either, so I'm not in either, so I gotta return the actual constructor here. Pure doesn't mean right. Yeah. Similar construction here. Pop. Your right unit. All right, so in this stub case, we're really just testing that this was called. We're not, kind of mocking up more complex behavior and telling our mock system that, like, in this case, in this test, we want to throw errors. In this test, we want this. We're being very, very simple here, and kind of deliberately ignoring them. We're using these stubs. We're just asserting that these things get called. We could, a better setup for this would be to allow us to like return left here sometimes when we want to and things like that. So just keep that in mind. This is not the best way of doing things. Type mismatch here probably. Yeah, so S there. That gives us a mock state. Let's look at that. So we have a function list of string to list of string. Hey, Count-Orin, welcome. Good evening. I'm doing great. How are you? Nice to see you coming back to the stream again. Imagine that's fine. Right. That's the problem. It should be like this. Yeah, and then that's better, yeah. That's this kind of, whatever, it's a helper function, not a big deal. So like in our IO action, of course, we would, be catching catching things here for adding subnets provisioning routers are HTTP errors, timeouts, retries, all that good stuff. Ooh, very entangled CPP code is not the most fun. Oh, yes, of course. You know, C++, I don't know. It's an okay language, but one of the things that makes me really happy about Haskell, one of the early experiences I had with it was when like I started seeing STM code and like how much easier it is to do concurrency and parallelism in a more principled way than you can in C++. Like C++ just requires a lot of discipline because it's just I/O everywhere. Everything's in I/O. Yeah. Well, sometimes you need a good medicine, right? Something to clear the palate. I'm glad to be of service, Count-Torin. It's what we're here for. I'm happy Haskell hacking. Right, so we have to return an either here. You know, this is just a prototype. I'm just making stuff up. So we can just return whatever. Gotta fix those lines, because those need dollars there. Clarify those. See about that. All right. Ooh, cloud ID. We'd have to, if we were doing a real one here, like doing an HTTP call, then we'd, you know, parse the response body and we could return a cloud, cloud router from that. Put the actual cloud ID we get in for this virtual router. All that kind of good old stuff. Okay. There. Got rid of all the type errors. We fixed everything. So how does our mock our stubs kind of work? Get our happy path stubs. All right, well then we just need one of these, because we're in the state monad has like these handy little functions for actually evaluating it in different ways. Right, we can just run, in our tests, we're probably just going to run it. We just care about the state, the list, that monads, the mock state. Right, we don't really care about the return value of our program here. We just care about that. It's the state value, the final state of the computation. All right, so evaluate state computation with a given initial and return the final value. Discarding the final state, we don't want that. Evaluate state computation given the initial state, return the final state. That's what we want, discarding the final value. Yeah. So we want exec state, the one. So what does exec state take? It takes a state computation, some initial state, S, and then we get the final state from it. All right, so the state we're executing, the state computation we're executing is going to be, say, like provision router. We could do provision router with, yeah, we'll just give it a couple strings. A, B. On our initial state, it'll just be like our mock state. The empty list initially. Okay. And so we get the final state, which will be provision router. There's our parameters A, B. And if we're writing a test suite against it, we can see that it was called. If we want something a little bit more, you know, whatever, we can have like, you know, we could flip the arguments around in exec state and have the initial state be the second argument, and then we can have like a whole state, several actions. We can have provision router command, then add subnet command, then we can test that the final state would have the expected list of these commands that are output to the system. Right. So the idea is that with this pattern here, we can provide different instances of M. And so we can have different interpretations of our monad that we run our commands in. So in prod, we'll actually call the cloud service. So it's going to have like a monad. It's going to have like logging and HTTP APIs and access to keys and things like that. Our sandbox monad, you know, might have a different one than prod, so that it accesses only the staging environment keys. Maybe it has more verbose debug logging that doesn't erase things from the logs and things like that. And then in test, we can have simpler in-memory monads that we can just assert that certain states happen or certain sequences of actions happen or certain error paths are triggered and what have you. Yeah. So Countdoran says, when the code gets so entangled, C++ loses all its promises of performance. Because everybody's too afraid to change the code and just patch over the old code. Right. Add another iteration over a vector. Yeah. Yeah, exactly. So, like, if you're not terribly disciplined with how you structure your C++ code, yeah, it can be pretty difficult and get pretty gnarly. I find especially with, like, all the different... because you have to assume I/O everywhere, and a lot of different effects, computation effects happen, like, you know, even just sharing memory or passing around other resources. It has... I'm not going to give you my thoughts about C++ on all of it, like, but yeah, I know what you mean, Corntorn. I feel you. Like, it's nice working in a clean C++ code base, but it's a lot of work to keep it that way. For sure. Whereas I find you could be a little bit more... You can get away with being a little bit more lazy in Haskell. You can't be entirely lazy with Haskell, but you can get away with it. Because even if you are lazy and you write terrible Haskell code, it is much easier to refactor, I find. Like what Countdoran's saying, like sometimes with C++ code you get too afraid to change things because you can't... It becomes difficult to understand where effects happen, and there's no separation between them. Whereas Haskell, you can totally rip things out and just be like, I wonder what happens if I delete this, and just see all the type errors come up. Fix all of those, and then you're like, okay, you don't need that thing. You can remove it. And just do it. And then your code compiles again, tests passed, and you're like, all right, cool. Ship it. I do love that about Haskell for sure. So, one of the things I think you do have to be a little bit disciplined about in Haskell is that when you're writing terrible Haskell, you can definitely write stuff that's not very performant, right, on accident. Behavior-wise works fine, but the dreaded, and this happens in C++ too, but like the dreaded space leaks can happen. Depends what level in the stack, I guess, you're working at. Well, yeah, I think all the other things still apply, though. Right, so now that's one way of writing this so that we can get this like different interpretation of our commands. Right, so when I'm doing the domain-driven design, and I've got those commands for my cloud service, kind of like bounded context. You know, our spec, our design gives us the names of these commands and kind of like the semantics of them, what they mean to our problem domain, what they should do. You know, we can handle those kinds of errors. With those M's, we've got to be kind of careful with like I/O, for example, because runtime exceptions can throw things out completely out of whack if you don't plan for those. But from a design perspective, that's one way you could do it. There's other ways to write this same thing. So you don't necessarily have to use a type class. And this is kind of like maybe one of those pseudo, I'm not going to say it's bike shedding because there are differences. And there are people who feel very strongly about this. But one of the things I do here is that we should kind of hold back from writing type classes in Haskell unless the thing we're writing a type class for has some kind of property to it. This is a property like a, I'll give it by analogy or by analogy, like commutativity in addition of numbers. It's a property you can test for in your type class if you're implementing plus for numbers, and like the number type class, right? That's a property you can test for, and there's certain things that must hold about commutativity. It means a certain thing, right? With a type class like this, what's the property of provision router? Like, it doesn't interact with, like, it doesn't mean anything other than like what it means to our like interpretation of like running these effects, these IO effects, and we're just using it really to abstract over the monad that's being used. But our like code in our program could just use provision router, and depending what context it's that provision router call is in, it could dispatch to state, or it could dispatch the IO instance or whatever. which is pretty useful. But yeah, like, so there's no properties really here. Add subnet doesn't relate to provision router in any way for this M, right? Other than these effects happen. Maybe there's something there, but I'm not terribly feeling it, so I don't know. This would be fine, I think. But another way I want to show you can write this is like the record of functions approach. Kind of gets you somewhat of the same thing. But instead of using a type class, we just use a data structure. And we might call this cloud service. We might call it cloud service handler. There's a cool pattern. There's another kind of Haskell pattern called the handler pattern, which I won't get into here. Maybe I'll link to it at some point. But basically, it's the same kind of idea. We have this type parameter M over the cloud service that we want to parameterize by. But instead of using a type class, we just provide the types for these functions here, right? And just like we were writing a type class, we can do the same thing. Getting super helpful advice. All right, string, subnet. And it has the same shape, at least in the definition stage. Right, they look very, very similar. Data cloud service prime M, data cloud service M. One uses data, one uses class. Right, and so how do we provide the different versions of M, the different instances of M in this case, for our cloud service? And this is where you provide an instance of this record with those collections of functions. So, like, run cloud service IO. There's cloud service prime of IO. Maybe just cloud service. I don't know. Anyways, that'll be an equal here. Cloud service I'm forgetting how to type because I'm like thinking about other things at the moment too. Kind of getting a step or two ahead of myself here. So Cloud Service Prime, then we just provide pretty much the same things down here, right? Provision router out IO. Add subnet IO. It's gonna, yeah, I forgot to put a tick on that. I'm just putting the tick on it to distinguish the names. We could even just call this like lowercase cloud service IO. Right, and so executing this cloud service IO now. Right, we have a provision router prime. That's, what does it take? It has that implicit argument at the beginning, right? It takes a cloud service prime as its first argument. We have a cloud service prime with IO that fixes the M to IO, right? It's cloud service IO. Now we can give the arguments, right? A, P, and that's how we would run it. Right? So that's another way you can do the same sort of thing. And now we kind of like free ourselves from that discussion, I guess, about when we should use type classes and when we shouldn't. It's kind of the same thing behaviorally, at least like when we evaluate these things, they kind of, we're using the same implementation in IO. It's just kind of like the way we're writing it, the way we're defining it is slightly different here. And the way we kind of run it too. Right, we can run provision router in the IO context almost directly here. And it's going to be the IO one here, the same thing. We didn't have to explicitly pass in a record of functions, right, to it. It just uses instance resolution to figure out which function I meant to run. And same when I do exec state here. Right, I'm not passing in an explicit record of functions. I'm just calling exec state on it, and by instance resolution, it's figuring out which instance of the cloud service type class I meant. All right, so that's two different approaches. Which one you should prefer, I don't know. Depends. I think they're both pretty good. I might lean towards maybe this cloud service one's record of functions version. If I was really leaning on kind of more an algebra-driven design to my code base, I wanted to be really kind of pure and are really strict about how we use type classes in our code base. But you know, we're going to take the risk of being slightly bit more verbose, passing those dictionaries around in different contexts. Dictionaries, records, whatever you want to call it. That's what I mean. Cool. Cool. Oh, the handler pattern. Yeah, let's just leave that for a second. That's useful to know about. This one, I've seen it before. I've seen it used in like a couple of code bases, but not very often. Not very much. The idea with the handle pattern, you can read all about it, is that like when you're setting up a program that has a bunch of resources that need to be acquired through IO, right? IO is kind of a very big monad. You can't carry things out of it. Once you're in IO, you're in IO. That's it. All your computations run in it. All our programs run in it, right? So the handler pattern lets you kind of like attach certain resources to a specific context, a handler for this context. Database handles, thread pools for making HTTP requests, whatever you name it. You put it inside the handler, and you kind of have this record of this. All your functions take the handle as a parameter. So when you want to execute creating users, getting user email in the examples here, they can just use what's available in the handle, and that's it. All right. So this would be kind of like, instead of using MTL or something like that to layer monads together, smash them together, you have handles, you do everything in IO or whatever. And you could even, maybe even what we're doing with parameterizing over the monad being run, so that you could do other things. As well, you can make it just easier to test without having to test in IO and lock out the world, so to speak. So that's a cool pattern as well that kind of I've seen used before, and I feel like kind of works fairly well with this idea. And it even has comparison to other approaches like stacking together. This is what like a monad transformer stack kind of function would look like, right? So which approach you use kind of depends how big your program is, how big your code is, on your team, you know, on the kinds of things that are important to your team, what sort of things you value, and what kind of approaches you have. How do you feel about your code? So yeah, that's the provisioning router, adding router. Let's pick an approach here for our prototype and just kind of wrap it up and see the whole thing kind of working. So let's add our interpreter back into our main loop here for the service. Let's go, I don't know, let's be super pointy-haired about it and cut out the type class stuff. We'll pretend that we have like the stuff all written out, whatever. We could do that for our cloud service prime with IO. We'll just get place that, not just in the region. Cloud service prime service. Okay, so we can imagine cloud service, mock cloud service, right? Our stub cloud service. Okay. Not too hard at this point, I hope. All right, with our state, whatever, mock state, blah blah blah, and we can implement that. However, we need to. Okay. So in right here, we get the command. This is, so from change has gone from the SQL query change, the insert updated delete, has interpreted it into our, into the range of commands that this service cares about. So we get a command. Now we need to interpret it into our actions here. So we can just case on that. So if it's the provision router command, right, it's going to get the router name, router MAC, do something there. We can interpret the add subnet command. It's going to have the router ID and the subnet mask. Or just the subnet. So we have 2 holes. Oh, where did I leave mock state in? Oh, sorry, that helper function. Doop, doop. And oh, sorry, we only I've been talking about add subnet this whole time. We only had, yeah. Rename router. Oops. That's what form change has right now. So let's forget about as subnet for a second. Rename router. That's a router ID, a new name. So our interpreter, we're gonna have to just fix that quickly. Rename router. Oh, we'll get rid of the ticks here while I'm at it. String, that's fine. String. Cool. You should be happy with access. Sync subnet was just an alias anyway, or maybe just a new type. So we'll just change that there. That should be fine. We probably don't need the show subnet. Because that's no longer add subnet either. Let's go ahead and change that. To rename router. Rename router. Missing you somewhere. My hole. Yes, there it is. Rename router. There it is. Cool. So back to our hole. Cool. So then, yeah, we just provision the router here. We give it our record or functions. So this is like the prod version here. Cloud service IO. And then the parameters. Router name. Router MAC. Let's pull that a little bit over so you can see it better. 1 hole left. Right, so we're getting that, and for our main loop, we're expecting IO unit. So we'll ignore the results here. We can even just use void on that, I think. We should handle it, but I just want to skip ahead a little bit. Just running low on time. So rename router. The cloud service IO. And that's going to take the router ID and the new name. Okay, cool. And everything should compile there, which is great. And we'll go to the project. And just build the service and just start booting everything up here so we can check it out. I'm going to run the database. Service. SQL start. Green part. That's good there. That's built. Cool. So I'm going to go in the projects here. I'm going to start the data plane part. So that's the REST API. And we had that with PostgREST. We run it like that. And then we run the service here that we just wrote. So, right, so that's going to get changes to our API now. So now when we run this and we get, we insert a new router through our API, we post to it, we should get this all printed out here. We do that. All right, we're just gonna have to like pretend that, you know, it's actually calling, say, AWS or doing what we programmed it to do. I'm calling that cloud API. All right, so we go to post, onto routers. We give it a nickname. Okay, so now, right, provisioning the router. So in real time, our control plane picked up that change on the database, picked up the insert into that table, interpreted it as a command to go and provision a router, and has executed that effect, right? It's gone off and provisioned it. It could do other things, like update the state of the router table in our database to show the user when they go to fetch the list of routers. You know, like update the state of it if we wanted to present that state into the table, for example. It can do all kinds of things, but the thing is we're reacting to that in real time by listening over the replication slot, which is pretty cool. So it's one way of using PostgreSQL replicant to implement like an event-driven kind of architecture or service for an application that was probably written on just a Postgres database that wasn't really designed to do this yet. Just a very decoupled way of doing it. Right, so there's wow. This has gone off, executed that effect, potentially had written it. Now we can rename the router too, right? That's gonna basically map to a patch request on that router. All right, so patch. All right, on routers. PostgRest. Sometimes I forget the syntax of it. Like I forget a lot of things. Because there's so many things. So many things. So there's PostgRest. I just want to check how the patch works again. Updates. Let's upsert, put bulk insert updates. Gotta be a patch. Patch. Okay. Yes, that's right. We had to use the... So they have this syntax here, very standard syntax across all of your resources. So we'll just have this colon ID, an operator for testing a qual. We'll just do equal, I think it's equal dot, and then our UID. So patch ID equal to, and then the router, the router ID that we want to patch. Like this. Oh, gone. Oh, just get it. There we go. Mice. Ugh. I don't know. I'm not a huge fan. Why is it doing that? I told you not to do that. Near. Snarky. Control C. Control V. No, it's not even picking. What the hell? Oh my gosh. Computers. Copy. Paste. What is going on? No. Oh my gosh, Firefox? It's this plugin, isn't it? Okay, well, let's see if I can copy it from here. There we go. Must be this browser plugin. It's not very good, but it is what it is. I just wanted to like show it so I don't have to like have little curl commands in my terminal line there to demonstrate this stuff to you. So if you know a better REST client that we can use, by all means, chat. Feel free to jump in if you've got a favorite you use. So we want like to change it to something more serious, following standard conventions. It's all lowercase. So we can patch that. That should be rename thing, but we can see that that's actually like this rename router effect, right? So now it's translated the update to that row on that table. So that is going to catch any update to the table in this mapping function where those two columns are present on that table in that schema, which is a pretty tight constraint. And if you're using something like PostgREST, that's fairly standard in how it generates queries. I think you're going to be pretty okay with that. That interpretation. Right, but as you're building up this map, it's important just to know like how those things map in to what events and what they trigger. Maybe in a bigger architecture, you might just use replicant to like stream these changes to logs, right? And then the service can just listen to the stream of logs and not even listen to replicant directly. Maybe even a durable store for those events, that kind of thing, and then get into like more of like an event sourcing or event driven kind of fan out kind of architecture, like a publish. So that's it, right? Pretty cool. I don't know. Hopefully pretty cool. That's one kind of thing we can use looking for. We can build applications like that. So kind of things. Well, thanks, Beavich. Yeah, I'm glad someone's impressed by it. That's good. So you can hopefully get an idea of where we can go from here, right? We could, once we get these changes into Haskell and we have these, we can provide interpretations for these queries. Maybe there's like more of a framework kind thing we can build up on this, where we can build a service that listens to these events and publishes to WebSockets. So if you have a front-end client that is your mobile app, for example, it can get like a nice WebSocket connection to your backend, do the basic REST operations that we know and love, very standard REST operations just on the resources themselves, but then get updates from the control plane as work is happening in the backend. So maybe I could build an abstraction on top of this that is like a blueprint to go provision a bunch of things. And that might take a while to do. But we could have these events published back into the stream by these little services that can update the mobile client, right? All kinds of things. We could write a service that keeps a cache of our current router's state warm based off the events as they come in. With really tight keep alive constraints and eviction. Right? You can evict very, very almost immediately and keep your cache really, really fresh, or queue up a few and whatever your need is, right? The idea is that these changes come in over the replication protocol in a streaming sort of fashion. The other thing I wanted to test and make sure of with replicant, though, was like, what happens if our service gets disconnected and some REST API calls happen? In the meantime, what I want to have happen, what I hope we did well with replicant, is that if I go and disconnect this service, right, it's not running anymore. Let's pretend it went offline, lost the connection, whatever it is, right? And we get another patch request. Oh, there's one too many W's. It should be that. Patch it again. It gets patched. We can post again to routers, create another one. Oops. All right. What I want to have happen is that these actions are still happening in the database, But the replication slot is now getting queued up with these changes. All right, so that when our service comes back online, it should start up where it left off in the stream of events. All right, so when I start the service up, it did. Perfect. Right. So I start the stream back up, it started where it left off in the stream, where it was last. Right, it picked up that these two events were sitting in, these two changes were sitting in the replication slot, waiting to be delivered when the replication client reconnects. We reconnected, we got those changes, we interpreted them, we ran those actions. So that's kind of the one thing we have to be careful of when using replication slots is on a busy data plane with a lot of changes coming in. If our services go offline and nobody's consuming those replication slots, like those, we have to configure those slots and like handle that situation, right? What happens when we get events? Do we let the slots be unbounded and just keep queuing up until we run out of disk space, or do we limit them, start dropping old events? What do we do? Right, so you have to be aware of that. It's a kind of a trade-off to this kind of design, I think. So BVich, using Postgres like an event bus. Yes, in this particular scenario, we're using it like an event bus. Yeah. So we're using replication slots, we're interpreting the queries that come down the line as into commands, events, and acting on those commands and interpreting those commands into pretend API calls into our cloud service. So that's what would happen in a disconnection event when our service goes offline. It's basically like we queue up the events in the replication slot, and then hopefully we reconnect really fast. We get back online real quick. We start reconsuming those events off the replication slot right away. Yeah. So be aware, design for it in your application architecture and all that kind of stuff, but that's one way we could use Replicant to do that kind of stuff. And that's pretty much what I got for this week. So we finished our prototype. Pretty good. I don't know what we're going to do next week. I was thinking of the office hours thing. Maybe if you, the agency, are interested, you have burning questions, Haskell questions, we can just have like an open Q&A, and you can come with your questions next week, and we'll look into your question and try to come up with a good answer for you and help you out. Good question. Swarm Collective. Is it possible to run multiple consumers? So if one goes offline, the other continues. So that... I'm not 100% sure. I think it's 1-to-1. But I do believe there might be a way for Postgres to do a broadcast publish to multiple consumers off of one slot. Excuse me. That being said, you could run your service on multiple slots, but then you would just be queuing up those events in those slots to those different services, and they would have their own slot name and everything. So you'd have to account for that. It's true. Replication streaming multiple consumers. So like a multiple replication situation. Theoretically, basically anything you can do with replication in this, any of those kinds of replication setups, you should be able to do with this. Yeah, or maybe a service that watches for a slot to become available. Right. So there is a way to do that as well. There is a query you can use to watch replication slot states. And you could have like a hot standby. Just waiting for that to happen. So if you just wanted a hot standby scenario, so you at least have one kind of always there, that's definitely possible as well. Yeah. So if we just connect to the database on the local host, I think it's PG replication slots. You can see that here. Our Nephil service. I'm going with Nephili. Our Nephili service right now is active. Right, you could have like I don't know what I call it like a dead man switch. I don't know if that's like an appropriate term or if there's a better one. But like this hot standby kind of thing where it's looking at this column every couple of seconds or whatever to go false. And if it goes false, then it goes, okay, the other one must be offline. Or if it goes false for more than a couple of minutes or something, then it'll pick it up. All right, so you can get failover that way. For sure. All right, another way you can do it is you can just also like remove the risk of it going down. Instead of writing your services directly listening to the replication slots, you can have like a very lightweight service that just republishes the changes, like interprets them to your events if you want, or just publishes the raw changes to like a durable stream. Right, then your services can run off of those durable streams, and those durable streams can be responsible for making sure the events get written out, you know, and can be replayed and all those sorts of things. You can have all kinds of failover scenarios for that as well. Concurrent readers, and all kinds of stuff. So there's multiple ways you can do these things, and the sky's kind of the limit. Yeah, so that's the prototype project for Replicant. I'm going to keep the office hours idea open. So if you're interested, you have a question, think about it, bring it with you next week. You can even reach out to me on Twitter. I'm at Agent Ultra. There, I'm on GitHub. I'm on the FP Chat Slack community. I'm on the FP Chat or FunProg Zulip community. There's one there. All over the place. And follow me there. You can also give me a follow here to get notifications when we stream next week, which is usually on Tuesday nights. If you're one of my YouTube followers, you know what to do. And bring your Haskell questions. I'll help you with your Haskell problems next week. We'll just talk Haskell stuff. Maybe we'll get started. Maybe we'll do a little bit of work on Replicant. See if there's anything we can do there to improve the library. There's some stuff actually I learned about in benchmarking this week at the Haskell Love Conference. So if you missed out on that, Haskell Love is an awesome conference that happens once a year. I met some cool people in the Haskell community that I now work with at that conference last year. And even in these wonderful times that we're in, they've been very stellar at running this conference. Those videos should be live soon from this year's conference at some point. Anyways, I found one on benchmarking that was really good. They gave me some ideas for Replicant. I know we did a little bit on benchmarking and Replicant, but maybe we can work a little bit on that next week if we don't get a lot of office hour questions. Yeah, we can talk Haskell performance and library performance and benchmarking and CI and stuff like that. So, thanks again for coming out and watching this stream. It's much appreciated. May your monads always be free. May your types always check. Storm Collective, it's too bad you couldn't join, but don't worry. The videos, they post them on YouTube. They should be up at some point. May your types always check. Happy hacking out there. And take it easy. Be safe.